tiles are manipulatives. They're used to provide a conceptual understanding for students to enhance their number sense, and it does provide that geometric interpretation of the algebraic expression or equation. They can also be used to model integers. Today we're going to focus on using them to solve equations, but within the equations we will be using them for some integer computation. Alright, so I'm going to switch over to my camera now. So everyone should have a balance mat or an algebra tile mat. It is a balance beam. This particular resource comes from the hands-on standard book for Algebra 1. It's located in the back of the book, and it's literally just a photocopy of it that I put into a sleeve. And these sleeves are great because you can write on them with dry erase. You can stick whatever you want on them. At my school, or at Dunlogan, we kind of keep the algebra tiles product mat on one side a lot of the time, and the balance scale on the other side.
Can I see what the other mat is?
Sure, it is this.
Oh.
It's on the back of yours, I think, or maybe not. No. Okay. So, all right. So we're just going to get started. So the first thing you want to do, if you've not used algebra tiles in your class before, you want to introduce the tile. So I think that another, a suggestion would be, what I suggest to my teachers is when you're going to use algebra tiles, the best thing to do is try to set up as much as you can ahead of time. Meaning, if you could get the mats out on the desk, if you could get 2 packs of algebra tiles, that should be enough to each student in your class. And if you're going to use the sleeves, then you want the dry erase marker and eraser out, obviously. And then when they come in, they're going to want to kind of play with them. And I think it's a really good idea to allow them that time to play with them on their own terms. So where you're not telling them to do something, but where they can just kind of go ahead and kind of manipulate the tools. We're going to be following along with this resource that I created. So I just want to make sure you have that. I wouldn't recommend using this particular resource with students. It's meant to be used for teachers because it goes pretty quickly.
Yeah.
But I would recommend maybe using the examples from it, because we're going to talk about in a little bit problems where you may not want to use algebra tiles. Okay. So the first thing, once they're done, they get that time to play with them on their own, you are going to want to introduce the tiles. So I always say, like, what's this? And what do you think they say? A square, right, and our square has 2 colors, blue and red. This is going to represent our x squared. This is an algebra, this represents x squared. The blue represents your positive x squared. Your red is going to represent your negative x squared. And then I also tell them, when we're working with linear equations, we're not going to be using x squared right now, but when we start to use them for multiplying binomials and factoring, we are going to be using this. So you want to introduce it to them. And then this is their x, okay? And I always show them that this is our x squared, and we can see that this is x, and this is x, which makes sense. That's a weird one. This is x, which makes sense because when you multiply x by x, what do we get? X squared, hence our x squared and our x by x. Okay? And the red side would be the negative, and the green side would be the positive.
How are you? I need a refresher. I'm missing a little bit.
Sure, yeah. All right, and then, once we've introduced those, once I've introduced the x squared and we're just solving linear equations with them, I tell them take the x squareds and put them back in the bag, because you don't really need them for today. So the last piece to show them would be the smaller square, which is yellow and red, and what do you think this would represent? The numbers, right. This is going to represent our integers, our whole integers, so it's going to be +1, and then a -1.
So which side is negative?
The negative is the red.
He's always red.
Right. That's the one color they kept consistent. Okay. All right. Another thing to introduce to them or to spend a little bit of time on is talking about making the zero pair or the additive inverse of 1. So if this is positive 1 and I put a negative 1 here, a negative 1 here, what does that represent? This is going to represent 0, correct. So this is what we call a zero pair. These are additive inverses of each other, and they make 0, okay? And then you've kind of covered all the basics part that they would need to know before they start working with the algebra tiles. Thank you, Andrea. I know this wasn't what you intended to do.
That's all right. I like it.
Okay. All right, so we're going to start with a very basic one-step equation. Here we go. And we're going to start with x plus 2 equals 6. Now, the great thing about this, when you use the sleeves, is I go ahead and have them write the equation right on the map. And then talk about what that represents. So what are we trying to say here? How would you describe this equation?
Some number plus 2 equals 6.
Exactly. Some number plus 2 equals 6. And this is on our scale, so these are balanced. So we know that whatever x represents when we add 2 to it must equal 6. If not, then our scales won't be balanced, okay, if we have a wrong representation of x. So we're going to represent this equation. So go ahead and try to represent that with your algebra tiles. All right, any questions on how to represent that? No. All right, we're keeping it balanced. We have a positive x, 2 positive 1s, and a positive 6 on the other side. All right, now we want to keep the equation balanced and we want to begin to solve it. So what do we need to do first? Well, I guess what we want to say is, what's the goal? What are we trying to determine here with this equation?
What x is?
What x is. We want to isolate the variable. So in terms of isolating the variable, what would be our first step to doing that? Right.
Yes.
Right. So we want to get rid of this 2. So we want to subtract 2. And there's 2 ways of doing that for this particular equation. Any ideas of what's one way?
Put negatives on both sides. Negatives on both sides.
Okay, so you both said, each of you said for the 2 ways. So one way of doing it is to do exactly what Jillian said, is because there's 2 positives on this side and 2 positives on this side, I can simply remove it, because that is keeping my scale balanced. And students will notice that can be done. However, can it always be done? If this was a negative 2, I wouldn't be able to do that. So it's not that is a wrong method, that is a fine method, as long as they can, when they're using algebra tiles, as long as it works. But you need to show them the other way by adding the negative 2 to both sides, because that method will always work. So in this case, we want to show that if we add negative 2 to both sides, I can make my 0 pairs here, and I can make my 0 pairs here. Oops, did I already do that? Yeah, sorry. I can make my 0 pairs here, and I get...
So you pair them up.
Right, you pair them up to make 0, and I get x equals 4. So you want to remove them, right, and then you have x equals 4. Okay? All right, let's try another equation. let's try a subtraction this time. Let's try x minus 4 equals negative 6. We'll go ahead and set that up. Sorry, all right, and so here we can solve it again using the two ways. So go ahead and solve it. So I'm going to add positive 4 to each side. Okay. And then remove it and see that x equals negative 2. All right, feeling pretty good about that? Okay. Yeah? Okay. Let's try a different one. Let's try negative 3x equals 9. Okay, so here's where we might see a little bit of misconceptions among students' understanding of the algebra tiles. So students should be representing this with 3 of the x's that are negative, each one of them being negative, and then a positive 9. On the other, positive 9, sorry, on the other side. Okay. One way of seeing students represent this initially is they might do something like this. How have I seen it? X and then this. Okay. Do you see where students would get that from? Okay. Or I'm sorry, this would be negative 3. So do you see where they would get that from? Okay, because they see the negative 3 and the x, and you've just spent so much time going over addition and subtraction ones. This might be how they represent it. So just make sure that you're clearing that misconception that this is actually x minus 3 and not negative 3x. Okay? All right, so we have negative 3x. We need to talk about what kind of equation is this represented here? Is it addition, subtraction? Okay, it's multiplication. And then we need to use the inverse of multiplication. So we're going to divide. So to show that division, I always turn them, I don't know why. But you would separate them because dividing is the same thing as splitting into groups, into even groups, right? And then a strategy students can use, let's say they don't know that there's going to be 3 in each group. A strategy they might use, and I've seen students use, is to kind of just count. All right, 1 goes there, 1 goes there. 1 goes here, 1 goes here, 1 goes here. Do you see what they might do? And sort of distribute those amongst each x evenly.
For you. Sorry.
No, you're fine. Sorry. Right. And then when you divide, you're just looking, so this is still representing negative 3x. You're not looking for negative 3x, you're looking for 1x. So you're going to divide. But here, we still have a negative x equals positive 3. We don't want to know what negative x is, we want to know what positive x is. So how do we get that x to be positive? Flip it over, exactly. Multiply by negative 1 or divide by negative 1 to get x equals negative 3. Okay. All right. Let's try, another one step. X minus 6 equals negative 4 this time. Go ahead and set that up. So this is an instance where that method of just like Jillian had suggested earlier, of just taking away from both sides, is not going to work. Do you see that? So they can't take away their 6. Sorry, this should be a positive 6. I'm sorry. That was my example. Okay, so you can't take away a positive 6 from this side, right? You would have to use those additive or those inverse operations here. Okay, we're not gonna. You can go ahead and solve that, but I just wanted to show you an example. All right, another example with algebra tiles, where you may not want to use algebra tiles for this with one step, would be where you're going to get a rational number. So if mine was 2x equals 5, okay? So students can represent that by 2x equals 5, right? But now what happens? When they start to do that division, is it going to divide evenly? No, I'm going to have this one extra guy here, right? So we know the answer is going to be 2.5, but I can't cut an algebra tile, right? So students have been cute and funny, and they're like, oh, Miss Farlotta, you can stand it up like that. You know, they just try to find all different kinds of ways to make it work because they want to, because they get into it. But it's not the best use for the algebra tile. So the algebra tiles are a great way, as I said in the beginning, to conceptually show what's happening when you're solving equations, but you kind of want these equations to end up looking very pretty. Rational numbers are not the best example for algebra tiles, so I would recommend getting one with a rational number. So another thing with algebra tiles to consider, and again, I'm a huge fan of algebra tiles. I encourage using them all the time. You're just trying to get them to that representation of the algebraic model. Would be division. So if I had x divided by 2 equals 6, again, to represent that, this is x. I like your faces like, wait, no, yeah, we can't do this. This would be a non-example. That would be x. So x divided by 2, I would need to divide this by 2 somehow, right? Which I don't encourage writing on the algebra tiles because it's really hard to get off, and then who knows what they're doing with it. But division doesn't really work that great with algebra tiles. But once you get them into seeing what's happening with always using the inverse operation, by the time you get to division, they have a pretty good sense. So we're going to move on from one step, but you won't see me demonstrate today any division with algebra tiles or any rational numbers. They're not the best use for that. Okay, so let's try a two-step. Let's try 3x minus 1 equals 5. All right, I'm going to start to move a little more quickly now so I can get through all the examples and so you can see the uses for it. So we are going to have 3 of our x's. Where's this little one keep coming from? A minus 1 and then a positive 5. Okay? This is a two-step equation, right? Because we're multiplying and subtracting in the same equation. And the first thing we want to do, and then students become familiar with this, they're like, we want to isolate the variable. So we need to get rid of this negative 1. Well, how do we do that? Add 1 to both sides in this case, right? So we're going to add positive 1 to both sides. Here they make 0. I can remove them. Now I'm down to my one step. So do you see how it conceptually shows them getting down to isolating x? And now here we would want to divide them into 3 groups. Again, you can use your strategy of separate, one goes here, one goes here. We're dividing, and x equals 2. Okay? All right? You feel good about two-step? All right, let's go on to multi-step. This is where the fun happens. Okay, so on the second part of your handout, on the second page, I get into multi-step equations. Let's try the first one. 4x plus 1 equals 2x plus 5. All right, so go ahead and represent that. Oh, these little ones are really throwing me off. Hi, Joan.
You're playing.
Some of my little ones here.
She's stuck. Okay.
Okay. So here to solve our equation, we want to start combining our like terms, right? So what I like to try to encourage is try to get your x's to one side and your ones to another side here. And algebra students, they kind of, it's great to see them work because they'll go back and forth a bunch of times. Just because they're like, but I can, and it'll work. Oh, sure, well, go ahead, do that. Just don't lose anything, like don't lose a negative or anything. Go ahead, Judy, sorry.
I can't remember, do we just flip them to show that we're moving them? Or do we just reuse?
I would use different tiles.
different ones,
Yeah,
okay.
I would go ahead and use different tiles. So I'm going to bring these
So
two.
subtract the two.
Yeah, so I'm going to subtract 2 from this side.
Got it.
And then I'm going to subtract 2 from this side. So,
What's the advantage of doing that rather
And-
than removing
okay,
two on both sides?
so we kind of talked, all right, so
Oh, sorry.
it's okay. Well, can I come back to that question? Okay. So, so these will be 0, negative x, negative 2x plus 2x. And then here, we need to start, these two will be 0 also, so these will leave as well. Now we're down to a 2-step. So we would subtract 1 from both sides. Now we're down to a 1-step. Again, we'd separate them into 2 groups. We know what 2x equals. We just want to know what 1x equals. And x equals 2. Okay, so going back, Joan asked a great question, which was, why wouldn't we just show this?
I understand the zero pairing, but
Yeah.
I'm also interested in having them see the balance.
Right. I mean, yeah, we talked about that earlier. In this, it will work. It doesn't always work. If this was like negative 4,
Right.
right, it wouldn't work. So what she was saying, what Joan was asking was, why wouldn't, just to show balance, and that is a perfect way, and I would encourage that if it can be done, is
It
to
lends
take
itself to the
2,
problem.
yeah, exactly, take 2, take 1, and I'm done. I've manipulated it and it's great and it'll work, and that is a perfect example, and I encourage students to do that. However, you want to model both ways, because if this was a negative 4, then that would not be possible. So you want them to understand both ways, but absolutely, if they can see that and keep everything balanced, I could take 2 x's from this side and 2 x's from this side, and a 1 and a 1, and they can keep something balanced, that is the whole goal. That's the whole purpose of solving an equation, is to isolate the variable and keep it balanced. So I would encourage that also. Okay, let's try another multi-step one. This one is going to be negative x plus 2 plus 3x equals a negative 4. Model that problem for us, so we'll have a negative x, positive 2, positive 3x, and a negative 4. I love modeling this kind of problem, and this is the one I find that I go back to quite often with students, because they tend to they rush to solve an equation and they don't start combining the terms that are alike on each side of the equation, and they just start moving things. And then, but when they see it in front of them, they want to combine them, because they're like, well, why do I have 2 sets of x's here? I want to have 1 set of x's. Well, that's exactly what you want to do when it's on paper. But if they haven't time to manipulate the equation, they do recognize that faster. So here, we would want to combine like terms on one side. So I have a negative x and a positive x here. I'm going to get rid of them. They make a 0 pair. Add 2 to both sides. Add negative 2 to both sides, excuse me. Divide. Sorry. And x is negative 3. go through it again or do another combining like terms one? Okay. All right, so now we'll get into the ones that include the distributive property. So let's try 2 times the quantity 3x minus 1 equals 4. Okay, so there's 2 ways of solving this particular type of problem. I love showing these also, because what I used to love to do with algebra students was I would put a really big problem on the board that was like -2 times the quantity, and I would put like 10 terms in it, close the quantity equals -6. And I would say, what do you want to do? And they would be like, I'm going to distribute the -2 to all 10 terms. And I was like, why do you want to do that? You don't want to do that. You want to divide by, but they don't see that. They're little procedural, little people that want to go ahead, but you want them to see the whole equation and how we can solve it. So here's a great way to model that with algebra tiles. So I'm going to show that. What this is saying is 2 quantities of 3x minus 1. 2 quantities of 3x minus 1. So here's my first quantity, equals 4. Can't forget about that, 4. Okay, and here's my second quantity. Okay? So here, because we have 4, which is a multiple of 2, we can divide both sides by 2. Because if I do the same thing like I would do if it was just 2x, I would separate these, and what I could do is just divide by 2, get rid of it. And now I'm down to 3x minus 1 equals 2. Okay, so you can model it that way. All right? If they don't see it, or they just want to solve it differently, what's another way they could do it? They could combine the like terms. So this becomes, it doesn't become 2 quantities of 3x minus 1. It becomes 6x minus 2, I just distributed, equals 4. That was always 4. And then they can, add positive 2 to both sides, add positive 2 to both sides. These cancel. I have 6x. I start, uh-oh, did I do something wrong?
Yeah.
Okay.
It's X is 1.
Okay, sorry, yeah. Oh, because I didn't finish my problem last time. Okay. All right. And then divide to get 1x, and x is 1. Both ways. Okay? It's really cool to show them both ways because it does get them thinking, can I start dividing by 2 on both sides? Let's try another one with using the distributive property. Algebra tiles are a great way to also just show the distributive property and take some time with that. It's not in our Algebra 1 curriculum, but it is in Common Core 7, so if you teach Common Core 7, it is a standard underneath equations and expressions.
Or would you use something, you wouldn't use that many steps?
No, I just have distributive property with maybe like 2 terms in it. Yeah, and then I would use this mat on the back. I would use the product mat. It's upside down now. I would use it like this way. Woo! Party. Like that. I would have my 2 and my x minus 3 or whatever, and then build it, combine it. These resources I've gotten from the Algebra, Hands-on Standards, Algebra 1. They're in the back of the book, and I think all schools have that now. So -3 times the quantity x minus 1 equals positive 12. So go ahead and set that up. I'll collect my algebra tiles. anyone know what time this goes to?
Till 20 of, then you start over again.
Okay. Am I, that's right?
Well, I'm confused by your
So we're
negative
gonna-
3, because I see 3 times the quantity of x minus 1.
Here.
Yeah,
Oh,
it should be read right.
I'm sorry, yes, sorry, thank you.
No, just checking to see if I
No.
understood it.
You're correct.
She must be trying to fool us somehow.
No, I'm not, I'm sorry, I'm worried about the time.
And then wouldn't the red turn green?
Right, and then your reds here would turn
And
green,
then the squares. The negative ones would be positive.
right,
It's the opposite of.
of, right. That would be the next step,
So,
so,
but that's not where you'd have the kids start,
well,
on the setup?
here, I would have them think about what's happening to that.
See, if they're setting that up the way you had it, to me, that would be they're setting up 3 times x minus 1.
Right,
And I want them to set up.
The
negative-
opposite.
Right, the
Right.
opposite of, which means they
So-
have to flip, right?
right, so I think either, it depends on how you want them to think about, like, initially, so initially it's 3 quantities of x minus 1,
Right.
but because it's a negative 3, it's the opposite of 3 quantities, so
Right.
then they would flip it.
So, you have the flip as a step.
Yes,
I see,
that is
I
what
see.
I would have them do.
Thank you.
That's how I would have them think about it, but if you think, if you think that they would do this on the first step, then that's fine too. Okay, and then from here, we would do which method? Or can we do, how do you want me to do it?
It just depends on what minus 1, what's going on. My kids would probably distribute it, because that's where they're.
Combine them together? Okay, so this becomes negative 3x's minus 3. Plus, it should be plus 3. Plus 3. It should be a plus 3. Where did these little ones come from? Sorry. It should be a plus 3.
And then removing the 3 from each side.
Right, and then you could,
Distributing,
right, add your
regrouping.
negative 3 to each side. Is that what you're saying, Joan?
Well, yeah, they would probably do the balance of removing it from each side equally.
Oh, yeah, or remove 3 from each side and birth 2. And then,
Regrouping.
right, 3 groups of, what do I have, 4, right? I don't have enough there. And then divide.
You should have.
Oh my gosh, so then have that right. Can we do that problem again? Because I'm being videotaped. They're gonna have to edit, edit and do this.
Hold on.
There's nobody there, there's just that. Alright, so negative 3 times the quantity x minus 1 equals 12. I'm gonna focus on this problem now. Alright, so to set that up, I would have students set this up as x minus 1 3 times for the first step. Okay, and then a positive 12 here, so 2, 4, 6, 8, 10, and 12. Okay. All right. Now, I would have them revisit this because in the parentheses is x minus 1, but we want to look at what is happening to x minus 1. It's being multiplied, well, we have 3 times, but it's actually the opposite of 3. It's negative 3, so we go to represent that, we're going to need to flip everything on this side over to represent what happens when we're distributing this negative 3. Okay, from this step, we can solve it multiple ways. You can combine like terms and remove 3 from each side to keep it balanced. Separate our x's. How's that guy doing it? Okay. Okay. And then divide. You just want x. And then you have to flip again because we know what negative x represents, but we need to know what positive x represents. And x equals -3. Another way of solving that same equation, so I'll go back to what it was. We had this. Well, once we did all those other steps, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So another option here would be to divide these into groups. So you would have an x and a 1 there, an x and a 1 there, an x and a 1 there. Start separating these. Right? Okay? This is just like I was showing you what students can do to see that if what's on the other side is a multiple, you can divide like this. Okay? And then you can start removing again, 1 from each side to keep it balanced, and flipping. Okay? So when you're using the distributive property, as long as this number can be divided by whatever you're multiplying your quantity by, you can represent it in that way. But then you should probably show some examples where you wouldn't be able to divide it into groups evenly, and you would have to combine your like terms on one side and then start using your methods that you use from the other side. There are some resources on the wiki. There are some great resources on the wiki. I've done podcasts for all of what you see here. So solving 1 and 2 step, introducing algebra tiles, solving 1 and 2 step equations with algebra tiles, solving equations with algebra tiles using the distributive property, and solving equations with multi-step equations with algebra tiles are all represented on the wiki with some examples on there if you need a refresher course. Also, the National Library of Manipulatives has algebra tiles on there, so you can have students go ahead and try it at home if they have the internet, or in class if you didn't want to get out the physical models of the algebra tiles. And then I, of course, will upload, send the PowerPoint and the resources as well.